So friends, we are on fifth lecture of this week 6, that is probabilistic security risk assessment, and today we will be discussing cyber security risk assessment. Since the topic itself is very has got a lot of detailing expanse, so we will discuss limitation only. um, why? Because hardware part we have already discussed, physical protection system and all. Now cyber security has got a major component of software and attacks on software. So so that part carries more bigger dimension. So we'll introduce this topic, and of course we'll discuss some models and methods, and of course mathematics of that also. But then students, if they are interested in cyber security, which is a hot topic as on today, they have to really make efforts to expand their reach or expertise, and you have a lot of publications. So we will prepare you for your ground for this, and then you can take proactive initiatives. So we saw in previous lecture that we have all talked about the physical protection system, but now we are talking about cyber physical system where software, Internet of Things, they become important. And again, the threat, vulnerability and risk has to be mapped on this system. PR and cyber security. So when we do probabilistic security risk assessment, that is catering to cyber security objective, the tools are Bayesian network. I think Bayesian network is one of the Bayesian approach was used in probabilistic risk modeling also, but that was for basically updating the data, but then the objective is similar, trying to reduce uncertainty using Bayesian data, and of course connecting the node. So in Bayesian network we have a node, concept of node also, like we have in Markov. Probability at event level is characterized by circle and or by box, and then arrows or transition probabilities are given. So something like that it happens here also. And Monte Carlo. Monte Carlo we have discussed in previous lecture, so this it will not be part of this lecture. So Bayesian approach, its fundamental will be discussed in this lecture. Fault tree, yes, we'll compare the fault trees and attack tree, and we'll see attack tree is at the core of security risk assessment, but a mapping will be done and seen how it's fit into the PRA modeling. Markov model, benefit and challenges in cyber security. Okay. So just it is a statement, just Bayesian approach is data updating, and Monte Carlo simulation have been already been covered in risk simulation module. Also Markov modeling has been covered in dependency analysis module. Only Bayesian fundamentals along with an introductory part of this module will be discussed. It is like a framework for this lecture. Major threat areas in cyber security are malware attack, like typical like Trojan. We have been seeing last 20 years this kind of virus which infect the computer, and from one computer to another computer through communication or use of devices, and then insider threat. Normally we thought security risk come from outsiders, but it becomes a serious matter when there are insider threats are there actually. So insider and outsider threat, they cause maximum harm, and that has to be seen. Phishing, social engineering, that means information theft, collecting data and all, and then distributed denial of services. There will be a flood of data which is coming into your computer, and it doesn't have any flood and traffic. So your own system becomes inaccessible, and then the threat starts from here actually. Your computer has been hijacked by flooding this information or made dysfunctional. Okay, and zero-day exploit. Zero-day exploit means there will not be any opportunity to take a corrective action. This is a worst case scenario. No action, you are helpless, and your computer not in your control actually. In probabilistic security assessment, each threat is assigned a likelihood of occurrence based on the plant specific or site specific or generic sources, as also from the expert opinion. So here we are talking about if we have a threat, its a frequency also should come. So how it will get? Experience is that the traditional deterministic approach tends to be incapable in evolving uncertainty, because even if I determine something today, tomorrow it will not be effective. So it is better to capture the uncertainty and base our decision based on this uncertainty. Bayesian belief network, it is a probabilistic network, and here representation is graphical. Okay, and then this network maps the dependency and the direction in which the normally it is acyclic. Like Markov model is cyclic. It is acyclic means circle will not close. Okay, you have one event on top A, B. They are marking arrow to C, but they are not like a cycle coming. So let us see what is Bayesian belief network. Bayesian belief network or Bayesian network. I think sometime it is its basic structure come from the directed acyclic graph where dependencies are represented. Okay, it is a graphical technique, as I mentioned, between dependent and so it might start with the independent event, but then there are events which are dependent and their conditional probabilities form. Bayesian algorithm is at the core of Bayesian network. So we will see what is the Bayesian model. Consider the plant specific data referred as evidence. So now let us say if evidence is represented by E, the data available on some same application in generic domain called priori, and the estimate is called posteriori. What we are trying to say here is, if we have some limited data with us, so that becomes the evidence number 1, evidence 2, evidence 3, okay, or evidence n. And then we have priori. Priori means some data which is available in open domain, and that is something like representative. But for my domain, whether it will be sufficient or not, so in that condition I use evidence and priori, okay, to give the estimate of posteriori. So dependencies are represented by directed graph. Now BBN applications, lack of data availability. There are some limitations here, and that's why they are used actually. Uncertainty capturing is one of the major objective here. Problem domain require handling of distributed tomography. If one computer is in my site, other computer is operating somewhere else, and there is an Internet of Things, so then it requires a distributed approach actually. Problem issues to handle acyclic situation. So here it handles through directed acyclic graph uses acyclic conditions. In cybersecurity modeling, data is often scarce. This is an accepted fact, and that's why these tools are required. In AIML, it is used to represent data. Okay, so this is the expanse of the Bayesian network, right from data updating to belief representation, Bayesian belief representation, and for a distributed scenario how it works, and for software component, yes, Because threats are varying, uncertainties are high, so Bayesian belief network is used in this one. Now, before we go to the details, let us understand what are dependent and independent event. Generally asking, dependent event is event which doesn't depend, outcome of that doesn't depend on any other event. It will be called as independent event. And dependent event, its occurrence will depend on some other event. Okay. So, in this concept is very important, and this concept is provide the basis for conditional probabilities. That means, an two events are dependent, so the conditional probability of A depending on other. We'll see it is coming in this. So, Bayesian approach works on probabilistic approach that independent and dependent events support of uncertainty evaluation making. Uncertainty in data and information management is critical to the decision making. Most of the decisions are taken, at the core of it, uncertainty handling is the major issue. And if we have a mathematical model, it becomes pretty clear and explainable that why a decision is being taken. So, Bayesian approach provides a mathematical model formulation of uncertainty by updating the existing limited knowledge called evidence with the priori, that is data available in, to provide the estimate of posteriori, that is updated data. Before we go, we must understand the difference between independent and, of course. Now, let us see, we are trying to understand there are two events A and B, okay, and they are represented like this. Now, I will read out probability of A given B. Probability of this vertical line is a given that. So, probability of event A given B. By reading here, it appears to be A is dependent on B. Okay, fine. Now, how we understand the concept of dependence? If probability of A given B is equal to probability of A. Okay, same statement we have used for explaining if the event is independent. That is, probability of occurrence of event A does not depend on event B, because it has nothing to do with the B. That is, so event A is independent and it will be called as independent event. But now let us say now, if A and B are independent, then probability of A interaction B, then what is this? This is for dependent probability of A given by probability of B. If both are independent, yes, if both are independent, then probability of A interaction B is nothing but probability of A into probability of B. What we do in the fault tree for AND gate, it is 90% of the time we take them as a independent event. This is assumption without explicitly telling. But suppose if they are dependent, then here in the Bayesian network comes, the formulation of Bayesian network comes, Bayesian algorithm comes, probability of A interaction, the inverse U is interaction, probability of A interaction B is equal to probability of A into probability of B given A has occurred. So, this is how we spell the probability of A. But suppose if the this particular, given that condition is not there, then it is an independent event, but here it is not. We are explaining the dependent event. So, okay, probability of B given A has occurred. Okay. Now, A interaction B, it can be written like this also, probability of B into probability of A given B. Okay. We know the Boolean algorithm, A interaction B is equal to B interaction A. So, now we got this formulation. You can see here both are A interaction B, both this equation and this equation, and this becomes the fundamental for Bayesian algorithm. Now, you see probability of A referred as priori, probability of, now here we have not taken probability of B, because E gives me a meaning of evidence, but otherwise it works like probability of B only. So probability of B, then probability of A given B is referred as posteriori. That means the estimate I wanted, okay, updated estimate. So probability of A interaction B is equal to probability of A into probability of E given A, or probability of what we did on the previous slide, probability of E into probability of A given E. We can equate both the terms. We can equate, and here our objective function, that is probability of A given E. Probability of A given E is here. If I take it this term to this side, so I get the Bayesian theorem. Probability of A given E is equal to probability of A into probability of E given A divided by probability of E. This is basically a normalizing term. We will see in previous slide. So please remember this. These are the conditional probabilities that we are handling in here. And now let us see how. Now suppose the evidence E is comprised of A1, A2, A3, N up to N. So so we can formulate this equation, probability of AJ, probability of AJ given E is equal to probability of AJ into probability of E AJ. Sir, there is one specific for AJ we are evaluating, and we have normalizing term which was probability of E was there here. So probability of E we read as a, because that is evidence available here. So I raised to power 1 to n probability of AI into probability of E given AI. Okay. So AJ is called the prior, what one input that we have, and now we are with that we are comparing. So you can see here this term probability of E and the bottom term probability of E given AJ and this summation term, it can be otherwise probability of AJ is equal to probability of AJ, but this is E term, so is coming here, and now is called the normalizing term or the factor by which the prior probability is revised. Okay. So so let us see. Okay. So we got the fundamentals of Bayesian network. Now simple case which is relevant to us, I have given the assumption also. Threat is independent variable, because threat does not depend on our any internal parameter, while vulnerability and risk are dependent variable. So this is the BBN network. So we have threat, starting from the threat, vulnerability and security risk. Now threat has have the value 0.25. So if it is true, if threat is there, that means 0.25, this is a complementary T, complement T, that is not T, is 0.75, 1 minus 0.25, 0.7. Similarly, vulnerability, if it is T is equal to, that is vulnerability is there, 0.8, probability is there, 0.8, vulnerability, sorry, so if threat is true, the vulnerability is 0.8, and if threat is false, then vulnerability is 0.3. Then the complement of this 0.8, 1 minus 0.8 is 0.2, 1 minus 0.3, it should be 0.6, 0.7, sorry, it should be 0.7. Okay. So we characterize these two here. Now security statement we have here over here. So all this computation go by Bayesian algorithm. So if no threat, no vulnerability, risk will be 0 or 0.1 estimation, whatever comes, and no risk is 1. Similarly, if there is a vulnerability, there is a threat, then definitely there will be risk. So it is 0.99 actually it is coming, and 0.01 is a not risk. For these two scenario 0.4, 0.7, so we have 0.3 and 0, and this will come out from this Bayesian computation. Now we have fault tree. Let us see how adequately it represents our threat. So threat, as we said, The, it could be either land route, water route, air route. We have only developed for land route. It could be insider. For threat to become a threat, it requires insider as well as outsider. So AND gate is there here. If I develop an attack tree, many literature it shows threat has been developed using the attack tree. Now you see the difference. If had it been an attack tree, I have to say here in one event insider and outsider threat. But here I am able to through AND gate I am able to combine, treat it explicitly insider threat and outsider threat. Insider threat, weak link, whatever is weak link, I am avoiding myself giving direct reference anywhere for reasons. Motive, what is the motive? Knowledge and physical information exists. So this generates a insider threat. All should happen. A single element will not work because it is a AND gate. Outsider threat, redundant barriers, root and attack capability. That only will enable outsider threat. So these two together will give. Now these are not developed, undeveloped event. So I have stopped here. But I can do my calculation here up to here, insider, outsider, if I have data up to weakest link. I mean, detailing is your option. If the data is available, we can stop here also because these are the events, and it can be characterized. So this is the fault tree approach for threat characterization. Now, one more example I have taken. I am comparing here the attack tree and fault tree. So here, attack trees, we know that since we are hearing for the first time, seeing for the first thing, let us characterize attack tree. Attack tree is a graphical framework like fault tree and event tree used in PRA. Attack tree approach is oriented towards information, IoT, distributed network, and requires cyber security approach for developing resilience or against security attack. As can be seen, like fault tree, attack tree also is a deductive. Actually, it need not be always deductive. It can be inductive also. It depends on your objective, what you are doing it. Okay. So like fault tree is from top to down, top to bottom. That means this, and there are events have been characterized. Let us see how it works. We have attack tree framework. This is one I picked up from generic source, attack tree Windows NT 1993. Virus infects a file, okay, and then it could be virus run as an administrator or as a user. There are two possibilities, okay. Like in normal language we talk, virus exploits the root hole, and virus runs by an administrator. There are two, then only the virus runs on the administrator computer, okay. So either exploits on its own the root holes or run by an administrator. Virus runs as a normal user. Other infected programs, because user are putting some files, things and all. So user downloads and runs. So here we have other infected programs. For this node has been downloaded further. Virus runs on an admin. Other infected programs, virus infects installed package or admin downloads the package and all that. Now see the structure. This in attack tree, this is called root node. Okay, these are called parent node. Why parent? Because these are the child node. So what is basic event in fault tree is a child node. What is intermediate even a fault tree is called parent nodes, and this is called the top event. Okay. So there is quite a bit of similarity, but linguistic terms are different. Okay. Now in fault tree, virus infection. See how the language has been changed. Virus infection can occur either virus runs on a admin or virus runs on a user. Exploitation, exploitation of root holes. Okay, we are writing like this. So here this term, and it ends here. So this becomes a basic event. Intermediate event, virus runs as administrator, virus run by administrator. Okay, and we reach the top event. But here the scene is, I have this data. Okay, and I have to reach a conclusion whether it is virus infects a file. So what is your objective function that defines, but structure remains same, top to bottom or bottom to top, both are open. Okay, so that's how attack tree is there. So here we can say attack fault tree approach to a great extent can characterize the threat scenario. Okay, and even represent our protection system. Now I talked about the Bayesian updating. Let us take a simple example to get the thing. We saw the formulation of probability of event A given evidence E, that is posteriori, and priori was probability of event A. Okay, so let us see how this simple example I have got it from Modera's book. Okay, I can say I have adopted it because not as it is. So 90% of computers to a company, the memory card supply in a computer production, memory cards are coming from two vendors in a computer assembly. 90% from vendor 1, okay, and vendor 2 supplies only 10%, and 97% are not defective from vendor 1, and from vendor 2 80% are not defective. They are not saying defective, they are giving data of not defective. Okay, so this is the problem, and what the objective function is, if a memory card was found to be defective on the assembly shop, what is the probability that it has come from A, that is come from vendor 1. Okay, so we will limit ourselves only up to here only. So now you know that the A1 is the probability that the it has come from vendor 1, A2 is the memory supplied by the vendor 2. If this is the case, and defective from A card supplied and one defective from this thing. So probability of A coming part coming from A is 0.9, okay, and probability of part coming from vendor 2 is 0.1, 90% and also 100%. Probability that it will be defective, the card will be defective given that it comes from A is equal to 0.03. 0.01 it should be. Okay, it should be 0.01. Okay, so some figure we have to change. So it is a 0.03 we are taking over here. Okay, okay. Defective is 97. So 97, 1 minus 97 is 0.03. Correct. Now probability of defective A2, that is 20% defective. So 0.2. We have got Bayesian formulation. Probability of vendor supplied part, they are defective, is nothing but 0.9 into 0.03, and same term plus 0.1, 10% defective, and it is 20% not defect, 80% not defect, or 0.2. So we get, and there is a probability of 0.57% that it is from A. Now how it suits our common basis when we do a numerical calculation, because after seeing the result we might say now that 90% of the parts were coming from vendor 1 only, vendor 2 was supplying only 10%. So probability coming from vendor, but then if this formulation is not there, how we will think, that is the question. Okay, and I think in open literature there are many problems you can see to understand the Bayesian, how it works actually, and how it works for Bayesian network, belief network. The conclusions are like that. Cyber security, the role and limitation of traditional approach to risk assessment. So, cyber security, one, is a very, very important phenomena, as it is cyber fraud is one of the important phenomena, and a improved approach is required to address cyber security issue for understanding the threat, not number one, giving its quantification. Even though the safety critical systems as well as the protection and defense in depth provisions, the cyber systems require an approach that can capture and manage uncertainty, as cyber attacks are ever evolving, as also method of attack on the command. So, this is one of the thing why we should use this probabilistic approaches. PRA framework is expected to be provide an improved framework for cyber security modeling, where apart from fault tree, event tree, role of attack tree and Bayesian belief network can be complemented. I mean, it is PSA or PRA network is open for any other tool. That node output has to be connected over there, and there are professional software that are available to do that actually. And why PRA software? Because PRA exists in many plants. So, if I use PRA, then I can compare on the same ground. There is a need of guide, of course. Though there are for cyber security, there should be more work to be done. For physical protection system, lot of work has been done. For sabotage, lot of work has been done. But cyber threats, it requires a focused attention.